These are the limiting reactant notes. It'll be helpful to have a periodic table and a calculator and the stoichiometry chart nearby. These notes start with a gram-to-gram stoichiometry entrance question. Feel free to pause the video and give these a try. We are going to reference the answers to these problems a little later in the notes. Here's a periodic table and the stoichiometry chart in case you need it. All right, so as we get into these limiting reactants, we're going to talk about how do we visually identify a limiting or an excess reactant. First, by just kind of looking at this analogy. You're throwing a barbecue and serving hot dogs. Each hot dog requires a bun. As we think of this in a reaction, just as a reminder that whatever is on the left side of our equation, those are our reactants. And then on the right side are our products, so what is getting produced. And so as we are looking at those, we are kind of considering that we have hot dogs and buns on their own. Those are our reactants, and then those produce a hot dog that is in a bun. So if you have 5 hot dogs and 4 buns, the buns are going to get used up, meaning that those are limiting. And we can see our 4 hot dogs in a bun here. The 1 hot dog that is left over and couldn't be eaten without a bun is called our excess. And so in this case, because a hot dog is a reactant, this hot dog is an excess reactant because it did not get to, it didn't get used up through our process of making hot dogs or our reaction. Another example, if you have 5 hot dogs and 8 buns, the hot dogs are going to get used up, which now means our hot dogs are limiting, but we are going to see we have 3 buns that are left over, and so again, those buns on their own are a reactant. They are helping to produce our product, and so those that are left over would be excess. So in this case, our buns are our excess reactant. This example uses a 1-to-1 mole ratio. We are going to look at how we can deal with this if we are doing a chemical reaction and how that applies with something more complex. So how do we visually identify this? Here's an example of nitrogen gas reacting with hydrogen gas to produce ammonia. Our reaction is here, and it is balanced for us. And so this question says if you have 3 moles of nitrogen, and we can see our 3 moles of nitrogen because those are the green atoms here. Nitrogen's diatomic, which is why they're in pairs. So we have 3 moles of nitrogen before the reaction, and we have 6 moles of hydrogen. Those are the smaller tan atoms there. 6 moles of hydrogen. Well, in order to produce NH3, ammonia, we need 1 nitrogen paired with 3 hydrogens. And so we can see those ammonias that are forming or being produced. And so after the reaction, we have 4 moles of NH3. Those are in those compounds. But of all the pieces we have here, we still have some of those nitrogens left over, meaning that after the reaction, we are going to still see nitrogens after the reaction stopped. So nitrogen is our excess reactant. And what is our limiting reactant? Well, we ran out of those hydrogens, which then stopped any more NH3 from being produced. So our hydrogen, or that H2, is our limiting reactant. And so as we talk about what can we visually see with these, an excess reactant is that reactant that is going to have something that is left over after the reaction. So the limiting reactant gets used up completely, so you won't see any of it left over. The excess reactant won't get used up, so some of it will still be visible after the reaction is complete, and it'll still be visible in its original state, or in its original form. So if we look here, and again, it's hard to see with just molecules. We're going to look at some examples of how we could kind of model this. But before the reaction, we have our blues and our pinks. After the reaction, we have our blues and our pinks that are joining up, but what limited more of those from happening is that we ran out of the blue. So our blue is the limiting reactant. Notice that that limiting reactant gets used up. We won't see any of it in its original form. We see no blues that are by themselves, but the pink is excess. We have some of those pinks that are still unpaired, and so those look similar or the same as that original form. Looking at this example here, we are looking at hydrogens and oxygens, and then after our reaction, we are getting H2O molecules. Well, we see that there are hydrogens left over, so those are excess. And what limited this reaction? Well, all of my oxygens got used up, and then the reaction had to stop, so oxygen or O2 is my limiting reactant. Our atoms and our specific molecules or particles are too small for us to actually see. If our chemicals have specific colors, we might be able, or distinct colors, we can sort of see what is happening or what might be excess or left over in a reaction in the lab setting. So that's what this one is going to look like. So in chemical reactions, we can see those excess if our reactants have distinct colors. So here is an example. We have C2O4H2, which is a colorless solution, and KMNO4, which is a purple solution, and those are going to react. MnO2 is a black solid, and all the other products are colorless. So again, our reactants are on the left of the arrow, our products are on the right, and this one said that our MnO2, that is a black solid. The rest of these are going to be colorless. So this says, sketch what the product would look like if C2O4H2 is limiting, and then if our KMNO4 is limiting. So no matter what is our limiting reactant, we're always going to have products after our reaction. So I'm actually going to just draw my products right now. I'm going to have black solid, so I'm going to just maybe draw like this, MnO2. So there's black solid. I also have colorless aqueous K2CO3. So we're going to just put, that would be a solution, so I'm going to have K2CO3 in there because that's one of my products. I'm also going to have H2O in there, and this says we also have CO2 gas. I'm going to put the CO2 above that kind of solution line just because that gas would be released. And both of these, no matter what is limiting, both of these are going to have products in them. If we start to think of our C2O4H2, if this is limiting, that means once this runs out, our reaction stops, and that means we would have excess of our other reactant. So that would make our excess KMNO4, meaning we would also see KMNO4 in with our products. And this says that that KMNO4 is a purple solution, so it's going to be in with those, it's aqueous, so it is in with those other things. So if we wanted to, if we had a clear solution and a purple solution, that means this is going to have a purple tint to that solution. If we sketch what the product would look like if our KMNO4 is limiting, we still have all the products, but if our KMNO4 is limiting, that means that our excess will be the other reactant, C2O4H2, and this said that is a colorless solution. So I'm going to put that in here as well. The color of that I wrote it doesn't actually change anything. If we don't have colors, we could also just indicate by saying this would be a purple solution. We could say this is a black solid. And so you can also indicate without colors, colorless solution, and just writing what we know would be occurring with that. All right. So this is how we can maybe do a reaction, and if I see that purple left over, that purple is my KMNO4, so that means that is excess. I didn't use all of it up, but the reaction stopped when my C2O4H2, my limiting reactant, ran out. Oftentimes, though, we don't have distinct colors, and it's best to rely on kind of the math or the theoretical values. All right, now starting to look at how we can determine limiting reactants algebraically. Here's that gram to gram entrance question from the beginning of the notes, and here are my answers. That 45.6 grams of aluminum produced 5.1 grams of hydrogen. The 59.53 grams of H2SO4 produced 1.2 grams of hydrogen. And we're going to actually reference these on that next slide. So having 45.6 grams of aluminum, so we were given that starting amount of aluminum. That was our first one here. That produced 5.1 grams of hydrogen. Again, looking for those grams of hydrogen. For our 59.53 grams of H2SO4, that is our calculation here, that produced 1.2 grams of hydrogen. And so as we look at comparing these values, we started with our two reactants. We started with an aluminum amount and a hydrogen, an H2SO4 amount, and looked at what each of those produced for one of our products. So which reactant produced less hydrogen? Well, 1.2 is smaller, which means that H2SO4 produced less. And so that means that is our limiting reactant in this reaction. And our limiting reactant is the reactant in a chemical reaction that limits or stops the amount of product that can be produced, and it's because it runs out first. So once all of this 59.53 grams is used to make 1.2 grams of hydrogen, the reaction has to stop. There's none of it left, which means that aluminum produced more hydrogen, and so it is our excess reactant. And so this, because we only have two reactants, we only have one excess reactant, but you're always going to have one limiting, and then everything else is going to be an excess on your reactant side. And that is the reactant or reactants in a reaction that are in excess or remaining after the reaction is complete. Once we've run out of our H2SO4, the reaction has to stop, which means we're not going to actually use up all of that aluminum. And that is, again, going back to our pictures, why we would see that excess reactant remaining after or in our beaker or whatever we were doing our reaction in. So how do we go through determining limiting reactants using stoichiometry? Well, we went through those steps in that warm-up question. You're going to complete a conversion of both given amounts. You might be given grams or moles of your reactants, and then convert to the stated product. So this one we just did, 45.6 grams of aluminum and 59.53 grams of H2SO4. What is the limiting reactant to produce that hydrogen? These two calculation problems, those were done in that warm-up question, and then we were able to just do that last step, which is to compare. Whatever reactant made less is limiting, whatever reactant made more of the specified product is excess. So let's look at a calculation here. If you have 140.5 grams of zinc with 90.5 grams of phosphorus, and it produces zinc phosphide, here's our reaction. Given the following equations and calculations, what would be the limiting reactant? And so we're taking those two starting values, those two numbers that were given, those are our starting values, and then we are solving both, doing a stoichiometry problem to end at the same spot. In this case, we only have one product, so that is the product it told us. So whatever product your problem is specifying, that's where you would solve for. So with this, we got that our zinc made 185.2 grams of zinc phosphide. Our phosphorus made 375.1 grams of zinc phosphide. And so we're going to compare. And that zinc made less, so this is the maximum amount that can be produced, which makes our zinc is going to be our limiting reactant. And that means that we would have excess phosphorus. So zinc is our limiting reactant, and our phosphorus is excess. We're not going to be able to use all of it up. If we want to sketch a model of what would be present after the reaction is completed, we don't have states of matter or colors for these, but that's okay. Zinc phosphide is our product, so we would definitely have in our beaker our product, zinc phosphide, and we would have whatever is excess. We would also have just phosphorus in there. We are not going to see any zinc because all the zinc got used up and limited our reaction. All right, let's go through and do this problem following that process for solving for limiting reactants. All right, plants create sugar and water using the following equation. If a plant is exposed to 4.52 grams of carbon dioxide and 6.08 grams of water, how much sugar will the plant produce? So as we are looking at a limiting reactant problem, we need to kind of break this into two problems from what we are given. Our first problem is that we're going to start with one of those given values, so 4.52 grams of CO2. And then we need to figure out how much of, in this case it's sugar, how many grams of sugar, C6H12O6, will that reactant produce? And notice CO2 is one of our reactants. So we're starting with a reactant value and ending at whatever product was specified, which in this case was that sugar. Our second part of this is that we are going to start with our other given reactant value, 6.08 grams of water, that H2O. And we also need to do a calculation to figure out, well, how many grams of sugar will that produce? Because then we are going to compare those two values with that. All right, so in this first one, this is a gram to gram conversion, so it will be 3 steps. So we've got 4.52 grams of CO2. Reference back to your stoichiometry flowchart or those conversion factors if you need. We first need to go from grams of CO2 to moles of CO2. And we know that 1 mole is molar mass. So finding the molar mass of my CO2, I've got 12 plus 2 times 16. That has a molar mass of 44. Next, I need to use my mole ratio. So I am moving from moles of CO2 to moles of that sugar, C6H12O6. And where do I get those values from? Well, I've got 1 mole of glucose or sucrose or sugar, and I've got 6 moles of that CO2 coming from my coefficient. Last step then is going to be to find our, go from moles of our sugar, so 1 mole of C6H12O6 to grams. And so then we need to find that molar mass. So that's going to be 6 times 12 plus 12 times 1 plus 6 times 16 to get that molar mass. And I got 180. And now we can go through and do that calculation, multiplying everything in the numerator, 4.52 times 1 times 1 times 180, dividing by everything in the denominator, divide by 44, divide by 6, divide by 1, and I got 3.08, let's just round to 1 decimal, so 3.1 grams of sugar is what we would get from that amount of CO2. So we took our CO2 value and we did that calculation. Now we do the same thing with that water value and find how much sugar that is going to give us. And I did that calculation here. And now we are going to compare our two values. We need to figure out how much sugar will the plant produce. So is it going to produce 3.1 grams or is it going to produce 10.1 grams? And we need to think of which one is going to run out first. And our CO2 can produce less, which means that how much sugar? The smaller of our two is the maximum amount that can be produced or can be made from the amounts of our reactants that we have. So that means that our CO2 is our limiting reactant. It's going to run out first. Our H2O is our excess reactant. We have more than we need. And again, that theoretical yield or the maximum amount we could produce is 3.1 grams of that sugar. If we want to sketch a model of the reactants and products that would be present after the reaction has completed, I know that I'm going to have my products. So I need to include both of my products. This one says the sugar is solid, so I'll make it look like a solid, C6H12O6. That oxygen is a gas, so I'll just put that up there in the beaker as well. And I'm going to include whatever is excess. I'm not going to use up all this water, and so I'm including that H2O gas in my model as well. All right, there is one extra practice problem here. Feel free to give this a try on your own and then come back and check your answers. I went through and did my calculations, but now I need to still go through and answer my question. Which is my limiting reactant? Well, my 67 grams of sodium made 80.6 grams of sodium nitride. My 90.5 grams of nitrogen made 536.5 grams of sodium nitride, which means whichever one is smaller, that is my maximum I can produce, my theoretical yield, and that means that whatever that was, that sodium is my limiting reactant in this case. All right. Practice is posted on Schoology. There is a worksheet. Check your answers using the key provided. You are expected to show work for your calculations on assessments. The limiting reactant check-in is also posted for you, and reach out to your teacher with any questions.